I am José Lopez Esteves, and I am with the ANSSI, which is the National Cybersecurity Agency of France, and I work in the Wireless Security Lab, which is the National Tempest Authority, and we deal with two main topics, wireless communication security and what we call electromagnetic security, which relates to the security of the information which is processed by electronic equipment and the risks that can occur when this electronic equipment is put into some specific electromagnetic environments. Um, the agenda for today: first, I will explain the leitmotif of the research and why we think that electromagnetic watermarking can help solving and complementing UAV neutralization. And then I will explain how we built the proof of concept on a commercial common off-the-shelf UAV. Um, and indeed, I will show that the first step is susceptibility testing in order to identify specific suitable effects that we could exploit in order to set up an electromagnetic watermarking um, system. And then I will show how we manage to embed effectively information into the target remotely and by exploiting effects of electromagnetic interference on the target electronics. So just a few words on common off-the-shelf UAVs and civilian UAVs. They are more and more used by law enforcement and defense organizations, and they also can be used for malicious purposes. As we have seen recently or in the recent years, many UAVs flying over critical facilities or flying during special events. Um, and one of the possible mechanisms to stop those behaviors is the implementation of a mechanism which is called the no-fly zone, and which is implemented into the UAV, the flight vector. And the no-fly zone is a kind of a blacklist of GPS coordinates into which the drone might not be able to fly over and nor to take off. So the main technique to bypass this restriction is quite well documented on the internet, and it's based on GPS bypassing uh, by adding and some sort of shielding on the UAV in order to inhibit the GPS signal. And there are also some hardware modifications which aim at spoofing the GPS position that are provided to the main CPU of the drone. So besides that, the neutralization of UAVs raises several issues, and there are different techniques that are considered, but there is no magical trick here, and there is not a universal technique that is emerging. And among the different technologies that can be deployed, radio frequency directed energy weapons are considered, and there are several products on the market that can do that. And most of the time, the main goal here is to desensitize or exploit front door coupling um, in order to perform some kind of jamming of the radio frequency communication links on the target, or try to simply take down the target. And in this case, the target will fall. And we thought that it might be interesting to investigate um, other effects and other ways to exploit the phenomena that occur on the electronics of the target when it is targeted by radio frequency directed energy weapons. And the idea that came to us was to try to embed information into the target in order to be able to prove that afterwards that the target has been part of the incident. And we think that that may be done using the electromagnetic watermarking technique that I'm going to introduce now. So the idea behind electromagnetic watermarking is trying to exploit some specific effects of electromagnetic interferences on the electronics to embed information into a non-cooperative target. And in fact, we are trying to exploit some effects which have specific characteristics. We are trying to uh, exploit effects that are highly reproducible and transient, and which have a benefit of a kind of a persistence mechanism, which will store the the information that the effect occurred, in fact, inside the target. If we refer to the classification of the effects by duration that was provided by Sabat and Nietzsche in 2006, it appears that the most suitable effects are from categories E and T. One important information while designing this covered storage channel is to know how much information can be stored at once. And for that, it's for determining that, we are trying to determine the storage channel capacity, and it depends on the write speed. So the write speed is highly dependent to the effect that is exploited, its appearance, its propagation into the target. So it is highly target dependent. It depends also on the persistence mechanism characteristics. So again, it's highly target dependent. So the write speed gives us an information about how many information can be embedded during a certain time. The storage capacity can be determined from the write speed and from the exposure duration. So this depends on the operational context, of course. And the total storage space is an information that has to be deduced from the target again and the persistence mechanism. So from this analysis, we understand that the electromagnetic watermarking is performance will be highly dependent on the target and on the operational environment in which the system has to be deployed. Just to give an example, here we have the target, which is put into an electromagnetic environment, which triggers a physical effect and which will have an impact, so a logical impact on the system logs. And by repeating this operation, one can modulate information directly on the system logs. So now that we understand a bit more what electromagnetic watermarking is, the question that arises is how to implement that, how to practically implement that. And there are several characterization steps that have to occur first. As you understood, we have to identify suitable effects from the categories E and T. And for that, we have to perform some susceptibility testing of the target. Once suitable effects are identified, the storage channel capacity can be estimated. And of course, depending on the operational deployment of the system, we will be able to answer the question, what do we want to embed inside the target, and how are we going to design an extraction system to get back to the information afterwards. So now I'm just going to present briefly how we perform fast susceptibility testing on our target, and some interesting effects that we observed. Our target is a civilian common off-the-shelf UAV, which is composed of a quadcopter flight vector, which includes an autopilot system with a lot of sensors, with different on chips, link. Um, there is a remote control, which spawns point the fire video of what the camera enclosed in the flight vector sees. And it can also send some coarse grain flight control commands, such as go back to the takeoff point or land. Some macro commands can be sent here over the Wi-Fi link. So on the Wi-Fi, the remote controller is the access point, and the smartphone and the flight vector are connected to the remote controller. There have been several studies on testing UAVs for electromagnetic susceptibility, and most of them focused mainly on the RF front ends. Um, some of them also described some motor malfunction and the ability to take down the flight vector. And most of the time, the way that these effects are observed is an optical, by optical means, with a camera or a hardened camera. Here, for our study, we decided to use an operating system centric effect observation method, which is described in the system design and assessment note number 44. And the idea behind this method is to place ourselves as the operating system could see the logical impact of the physical effects. So to apply this method, it is required to first identify software observables, which will give us information about the logical symptoms that I mentioned. And the second step is to be able to perform a software instrumentation of the target in order to gather this information in real time during the tests. So the first step was to identify the software interfaces which give us valuable information about the underlying phenomena. And regarding the front door coupling interfaces, the strategy has been to monitor everything that gives an information about the health status of the communication interfaces. And regarding the backdoor coupling path, we went after every information coming from the sensors, and also any information giving an idea of the operating system state. The second step was to find a way to access to this information and to automate the access to this information by running our own monitoring software on the target. And this required some analysis of the target and a bit of reverse engineering. So first we performed the hardware reverse engineering, identifying the different ICs, the sensors, the memories, the debug ports. uh, Extracting data from the memories gave us access to the firmware, and by analyzing the firmware, which was uh, as an OpenWRT, which is a common Linux distribution specific to access points, to Wi-Fi access points, we were able to go through the system configuration, the system logs, and to analyze the piece of software that was added by the vendor in order to inside the flight vector. By analyzing the vendor software, we found out that there was a serial protocol which is really similar to CAN bus somehow, and which gives access to raw sensor data with a high data rate. And by analyzing the mobile application, the Android mobile application, we got all the information needed to decode the serial protocol and to interpret the values coming from the raw sensor data. And that way, we had the means to access uh, to a lot of information coming from the sensors, raw data from the inertial measurement unit, information about the attitude of the aircraft, information about the radio frequency communication links, and so on. So the main idea to begin the susceptibility testing is to rely on the information that we gathered from the previous step, to get high privileges on the target, to modify the firmware, and to add our own code in order to gather the observable data that we want to get, and to redirect this data to a remote monitoring computer that will stand outside of the Faraday cage during the tests. And this provides us with a means to perform real-time observation of the impacts on the collected information. Of course, we are restricted to the impacts on the observable that we instrumented. But still, we saw some interesting effects, and the first result I want to share is the effect on the battery temperature sensor reading during parasitic exposure. And what we can see here is that when the parasitic signal is present, there is an impact on the temperature that is interpreted by the system on chip in charge of digitizing this information. And another interesting information here is that the magnitude of the effect is related to the magnitude of the parasitic signal. Another interesting result is concerns a value that is called vertical speed. And I remind you that during the tests, our UAV is laying down on a table, and we remove the propellers so it cannot fly. And here we see that during parasitic exposure, um the sensors in charge of gathering the vertical speed information are somehow messed with, and the information that is derived from there is the altitude offsets. And we see that the aircraft thinks that it is going up and down uh, because of the effects of the, the electromagnetic environment on the target electronics. So in this phase, at a glance, we saw alterations of the roll, pitch, and yaw angles values. We also saw effects on the embedded serial links, and of course, effects on the radio frequency communication interfaces, which opened some interesting perspectives. Tricking the inertial measurement unit sensors could lead to somehow uh, control a little bit, at least, the flight path. The effect on the battery temperature could trigger a safe mode, and when UAVs are in safe mode, whether they land where they are or they go back to where they took off. And some of the effects that we observed seem suitable for performing electromagnetic watermarking. So now that we gathered a list of effects and we identify the effects that are suitable for electromagnetic watermarking, how do we design an electromagnetic watermarking system? On our target, we were somehow lucky because there is an interesting persistence mechanism, which is called the flight logs. And in fact, uh, there is a lot of data, in particular raw sensor data and information about the radio frequency front ends, which is stored with a pretty high sampling rate on the UAV. So as we saw that we are able to impact the raw sensor data and the the radio frequency front ends, we could use that to insert information into the flight logs and afterwards extract the flight logs and get back to the information that we inserted. So the testing process, the identification of the effects has already been done during the susceptibility testing. And we focus on the effects that are suitable for the electromagnetic watermarking and that are logged in the flight logs, and our persistence mechanism will be the flight logs. So after the test, we extract the flight logs and we try to find back our information in order to characterize the storage channel capacity. As an example here, I present results again on the battery temperature sensor, which in the flight logs is sampled only at 1 hertz. And if we, according to the Shannon-Nyquist theorem, we can assume that we need at least 2 samples per symbol to get a reliable communication channel. And this gives us half bit per second, and half a bit per second means that to store a byte, we need 16 seconds. And in 16 seconds, a standard common off-the-shelf UAV might fly over 250 meters. So we need 250 meters to embed 1 byte of information in this case, if we decide to exploit this specific effect. A second interesting effect was on a value called vertical acceleration. And we saw that during parasitic exposure, a 15 hertz component is added to the signal, to the Z acceleration signal. The vertical acceleration is sampled at 250 hertz by the flight logs, which is much more than the 1 hertz of the battery temperature. And under these conditions, in order to insert 1 byte, the flight vector will cross 18 meters. Along with the vertical acceleration, this 15 hertz component uh, was also observed simultaneously on two other values, namely the pitch and the roll angle, which are also sampled at 250 hertz. And this brings up an interesting feature because it will help to identify more precisely the presence of our embedded watermark, because those three values are not supposed to evolve the same way at the same time. So the appearance of this 15 hertz component at the same time on the three values gives us confidence about the fact that we are facing our embedded watermark. So to conclude, about electromagnetic watermarking, the idea is to exploit some specific effects to embed information into non-cooperative target. It's a non-invasive way to embed information. However, there are a lot of technical challenges that are raised in order to practically deploy such a system. It's highly target and context dependent, and it requires to identify persisting impacts of the physical effects of electromagnetic interference on the electronics. The idea of applying this concept on drones, it was a good idea because of the persistence mechanism implemented by the flight logging system. But it raises also a lot of practical application challenges because UAVs are flying objects, so they evolve in 3 dimensions, and they evolve fast in space and time. And for these reasons, it might be very challenging to bring them in the specific electromagnetic environments required to trigger the effects that we identified here. However, it might be an interesting way to complement the other neutralization techniques. And again, we think that it might be interesting to generalize the technique, maybe use other ways to other physical perturbations. There has been some literature about perturbations on the sensors by using high power acoustics, for example. So maybe mixing the techniques might be a good perspective. And also maybe um, using several effects at the same time in order to perform some kind of multiplexing to increase the storage channel capacity. I thank you for your attention, and I'd like to thank Emmanuel Cote and Chauki Kasmi for their participation in this research. And if you have questions, I'd be glad to answer. Thank you.
Thank you very much, Mr. Lopez. Very interesting talk. We have a lot of questions here in the from the audience. So, but we have enough time. So I don't know if you want to. Are you able to read them? So the first one.
Yes, sure.
Yeah. So
Um,
if you mind, please.
so there is a question. Is the AM square test wave standard for testing, and are there other types of waves used for testing purposes? Uh, how can I answer precisely this question? Yes, of course, there are other types of waves used for testing purposes. Um, However, the reasons that we decided to go on these waveforms for the tests is that we think Here at ANSSI, we focus on lowering on the lowest attacker profile, and we have the feeling that the AM square test, uh, the AM modulated CW, is a kind of narrowband signal which might easily be generated by an attacker using some standard um, free, easily available software-defined radio, for example. So, and it has shown to be uh, kind of effective in our testing conditions. But there are, of course, other waveforms that are standardized.
Okay.
The signal power, yes. I don't have the figures, exact figures here, but I can share the test setup. In fact, we have a signal generator, um, which will operate between, let's say, minus 10 dBm and 0 dBm. And we use a 50-watt amplifier. We in the I don't know if you still see the presentation, but
Yeah.
in I tried
Yes.
to give here a rough measurement, a coarse grain measurement of the field magnitude. But as we are running tests in the Faraday cage, which is a reverberating environment, our measurement of the field magnitude is not really precise. However, here we were mainly focused on the effects, and we just wanted to have an idea of the field magnitude, but not the exact field magnitude. Um, the next question is why the modulation frequency is 8 kilohertz. In fact, we tried different modulation frequencies. And again, the main limitation here is the testing time and our testing equipment. But to be honest, 8 kilohertz, again, was against this target precisely a frequency that gave us satisfying results pretty fast.
Okay.
So can a model be built to find the golden signal to make it applicable to multiple targets? There are several questions here. Um, so for this question, um, I don't know if a model can be built to find this golden signal uh, because it requires, it is highly dependent to the target, physical layout, uh, and electric layout and electronic layout. So I don't know, I cannot imagine right now a way to build a model to reach that goal. But it's an interesting objective, I guess. Um, Earlier in the slide, I mentioned law enforcement and forensics. Uh, yes, but it was not, well, I just mentioned that law enforcement agencies are relying a lot on civilian common of just the shelf UAVs. And this justifies the need to understand um, and identify the way those devices behave in specific electromagnetic environments in order to be able to perform the hardening, find good hardening strategies. From these tests, have there been any study on hardening strategies? Not on our side. but it might be further work, I guess. It's yeah.
Yeah. Okay.
Oh, Mr. Shukov, did you study the dependence of UAV susceptibility on position regarding to RF source? As we see, the EMI primarily affects on signal and power lines, and then directly on PCBs or on ICs. As the cable are quite short in UAV, the effects can vary pretty much. Yes, I guess so. Um, it's a good question, and I guess if we wanted to run an exhaustive susceptibility testing campaign on the target, it would be necessary to make the target rotate regarding the RF source in order to change the incidence angle and the polarization of the source. Um, but in order to design the electromagnetic watermarking system, we just focused on the, the, the quickest effects that we could see. So our intention here was not to to be exhaustive regarding the susceptibility testing part, but it would be very interesting to do that and to try to then um, use the knowledge we gathered by reverse engineering the electronics and the PCB in order to try to correlate the the field polarization, for example, and the position of the UAV where the effect is stronger.
Okay. So
Is
after
this
that
work
question,
published already? The answer is yes. Uh, yes, last year it was Asia EM, and we are also preparing a system design and assessment note on the topic. For how long does the UAV save the flight log data? Won't it be deleted on the power down? It's a good question about the operational exploitation of the watermarking. Uh, it depends on the target, I guess. Uh, but as far as I know, um, the main the most common UAVs, civilian UAVs available, um, keep the flight logs until the next flight. And there is I think that uh, a Chinese manufacturer just keeps the flight logs until the storage device is full, and then it rotates the logs, so it might stay a very long time.
okay.
Mr. Parmentier, thank you. I, I mentioned in the introduction that I were looking for reproducible results. Reproducibility depends on RF excitation. Can you tell us what kind of RF excitation you considered in your susceptibility laboratory tests? Plane wave, random field in moisture chamber? And finally, will you have the opportunity or capability to test the drone in real flight conditions? About the first question, I partially answered already this question. Um, as I was really focused on um, the the first effects that responded. I didn't really try to to be exhaustive and to find the best RF excitation and to be exhaustive on the effects identification for many reasons. Here we are an information security agency, and we do not have equipment that that is suitable to perform exhaustive susceptibility testing. We are really focused on the information security issues, and so I think this part could be a collaboration, maybe with an external, a third-party laboratory. And again, the opportunity to test in real flight conditions, I wish I could. And here again, we are limited here. Um, we do not have the equipment to do that. And I will give the same answer. I think it might be a good collaboration to build. And even if I am not part of the project, I would be really interested in knowing the practical challenges and how they can be solved, and also the practical results on the field.
Okay.
Uh, may I continue?
Yes, we have, I think, for another two questions maximum, so it's
All
okay.
right, I will then answer them as they came, first in, first out. What could be the drawbacks of electromagnetic watermarking? As an example, could there be a permanent destructive effect on the UAV? Yes, of course. And one of the challenges will be to maybe find the limit um, of the right electromagnetic environment in order to be able to trigger the electromagnetic watermarking without uh, taking the flight vector down, or without destructive effects. But this is if we want only the electromagnetic watermarking. And I think there might be another option, which is to consider that it it might be probable that the the electromagnetic watermarking efficiency range, if I may say that, um, might be located just um, a bit further than the destructive effects range. So that's why I thought it might be a complementary technique. Uh, and if you see that this way, um, if you have a neutralization device which is not able to neutralize, to take the UAV down, there is still a chance that the watermark has been embedded anyway.
Okay. There is
Uh,
one more.
Dr. Giri,
No, this one
it's a
for
question
patients.
for Larsole,
Yeah.
for Dr. Fichte. Okay. Um, Thank you for the informative presentation. It is possible to overcome backdoor vulnerabilities of UAVs. What are ways you find effective in doing so? If not, what precautions do you recommend taking in preventing undesirable control of a UAV? Um, well, thank you for this question, which is a very broad question, because uh, we would have to define what we call a backdoor vulnerability. Um, so I don't know how to answer this without asking for precising a bit more the question. If we talk about information security related backdoors, um, or if we talk about um, perturbating the sensors in order to take control, and of course the the countermeasures are not the same. I don't know if I answered this question right.
I think it's a very broad question. Perhaps if the if the people that ask the question can contact you, you perhaps can
Sure.
exchange.
Anyways, in the slides, I'm sorry. I will put my email address back on the screen, and I will be glad to answer all the questions and to interact more on this subject by email if you want.
Excellent. Thank you very much. Very interesting talk. Hope to see you next year here in Abu Dhabi during Asia EM Euro EM conference.
Oh, I
And
hope so.
for attending and giving your presentation. Very informative and very interesting. Thank you very much.
Thank you very much.
Thanks.